Hi students, coming to the next topic, parallel priority interrupts. So in this case, we are going to observe here parallel interrupt sources. So this priority decoder is received the highest priority interrupt signal from the various sources. So how this CPU will respond with the help of this block diagram. So CPU will respond to the highest priority signal out of availability of the sources. In this case, here we have interrupt register and mask register is there. So with the help of masking register, we are going to mask all the binary values. Before going to explaining this concept of parallel priority interrupts, let us see the previous case. That means this is the daisy chain priority requesting service. That means here in this block diagram, device 1 is the highest priority compared to device 2 and device 3. Device 2 is the lowest priority compared to device 1, highest priority compared to device 3. That means this is the increasing order. That means the priority is increasing order. In this case, any one of the device is requesting the service only. Any one of the device is requesting service to the CPU. So here either device 1 is requesting service, that time the CPU will respond to the device 1. So if device 2 is requesting some service, the CPU will respond to the device 2, but in the priority basis. First the CPU will check the interrupt signal is generated from the device 1 or not. If it is not generated, the cursor goes to device 2. So if device 2 is checking the interrupt request is generated from this device or not, if it is not generated, the cursor goes to next level, interrupt signal is generated from the device or not. So here at a time, because for example, if device 1 is requesting some service like this, so if it is a logic low state, the CPU will respond that particular signal, requesting signal. Again, it is a respond through this interrupt acknowledgement signal. With the help of PI, it is equal to 1. So PO value equal to 0. That indicates this acknowledgement signal is blocked by this device because this device is requesting some service. But suppose if device 2 is requesting some service, so device 1 is not requesting some service. In this case, device 3 is not requesting service. This device 2 is requesting service. So if a CPU will receive this requesting signal, so with the help of interrupt acknowledgement, the service will respond like this. So PI value equal to 1, and it checks the device 1 is requesting a service or not. In this case, device 2 is requesting, so the device 1 is not requesting some service. So that PO value equal to 1. If it is equal to 1, that indicates that acknowledgement signal is passes through the next level of the priority device, that means device 2. So if it is generated, that PO value equal to, it will maintain, that means 0. So that in this case, PI value equal to 1 and PO value equal to 0. That means this acknowledgement signal go through this device 1, device 2 is holded. That means blocked by this device 2 because this service is requesting some service. So this is the way we are going to respond the interrupt requesting service from the various devices in serial manner. So, but in this case, in parallel priority interrupt level, here parallelly we are connecting interrupt sources. So in this first one, this interrupt register has a 4 bits and mask register has a 4 bits, 0, 1, 2, 3 and 0, 1, 2, 3. In this case, disk drive is connected to first place. This is highest priority, so that this is connected to 0 place. So coming to the decreasing order, priority, printer is the second priority, reader is the third priority and keyboard is the fourth priority. So these 4 bits associated with mask register. Every time if interrupt request is received, that signal, that particular device register value is held by logic 1. This masking bits is generated from the mask register that respect to mask register value. That means disk is connected to 0 place, so that this is associated with 0 place. This mask register 0 place. If printer equal to 1, that mask register equal to 1. These two are the associated. Reader equal to 2 and mask register 2. These two are the associated like this. Keyboard 3 and mask register equal to 3. So in every cases from the interrupt register and mask register, these respective values is connected to an AND gate. The AND gate output is connected to input of the priority encoder. Priority encoder, at a time any one of the one input is active. If it is active, that particular priority encoder output will be generated in the form of binary values x and y. So if interrupt signal is generated, that time this IST value should be hold by, that means 1. That means it is interrupt is generated, that line goes to logic 1 state, that logic 1 will hold by the IST. So with the help of this AND gates, we are going to generate some interrupt to the CPU. So in this case, let us see the operation condition. First one, assume here this is the CPU. In first case, coming to the operation in first case, first one, so with the help of this parallel priority interrupts. So suppose if disk is requesting some service, so that time with the help of this mask register, this value goes to logic 1, this value goes to 0, and this value goes to 0, and this value goes to 0. This mask register will provide this value equal to logic 1, and this is 0, and this is 0, this is 0. With the help of this masking bits, we are going to generating interrupt signal. So with the help of inputs, that means this is the logic 1. This logic 1 value goes to input of the AND gate. Same logic 1 will receive like this and place it onto this input of this AND gate. With the help of this two inputs, this AND gate will generate the output equal to 1. If it is a 1, this I0 is enabled will receive the interrupt request. If I0 is received interrupt request, this output of the priority encoder will goes to, that output goes to at a time 0 0. If it is 0 0, these two buffer, these two inputs are, that means interrupt signal is activated in the form of I0. In the second case, if the interrupt request is generated, xy values are goes to 0 0, that time this interrupt status flip-flop is enabled equal to 1. Interrupt status is enabled equal to 1. That time interrupt enabled is automatically goes to 1. If interrupt status bit goes to 0, that time interrupt enabled goes to 0. If it is 1, automatically this value will hold logic 1. So with the help of this logic 1 for this AND gate, and with the help of this interrupt to enable logic 1, we are applying these two inputs to the AND gate. So AND gate inputs are 1 1, this AND gate output equal to 1. If it is a logic 1, that indicates this is the enable line, that means the interrupt signal is requesting to the CPU. Until unless CPU will not receive any interrupt request from this device. If it is a received interrupt request from this line, that time CPU will respond through this interrupt acknowledgement. If it is received, that means if it is recognized, CPU will respond through this interrupt acknowledgement signal. The interrupt acknowledgement signal is given to this AND gate 1 input. The remaining two inputs are needed here. That input, the first input is taken from the IST value, and the middle signal input is taken from the interrupt enable. So with the help of these three inputs, the AND gate output goes to logic 1. If it is a logic 1, this enable is given to some triggering. So if enable goes to logic high state, then this particular vector address will generated. With the help of that interrupt signal XY status bit, the complete vector address, this register will provide the vector address. If vector address is generated, that vector address is valid, that means vector address is transferred to the CPU. After receiving the vector address, CPU will send that means transfer to the cursor goes to the particular location. That means in interrupt procedure, this is the main line execution. So this is the subroutine execution. So the cursor is executing in sequentially. If interrupt is occur, that means the interrupt goes to another location, that with the help of vector address only. This generated vector address is used to transfer the cursor like this. That means if vector address is received by the CPU, with the help of this address, the cursor goes to that particular location. That means we are using the subprogramming instruction. So this address is the vector address. So cursor goes to that vector address and it starts the execution from this instruction. After completion of all the instructions in the subprogram or interrupt service routine program, again cursor goes back to the mainline sequence and it starts the execution from this instruction. This is the way we are going to process the interrupt sequence. So this is the first case. In the second case, suppose if at a time this interrupt register, at a time this parallel, with the help of this parallel priority interrupts, at a time two devices requesting some service. That means this disk is requesting some service and this reader is requesting service. With the help of these two sources, we are receiving at a time two interrupt signals of this, two interrupt received signals. That time this interrupt register is making this values equal to both are logic 1 1. Remaining two values are 0 and 0. So with the help of this mask register, so it checks which is the highest priority signal is received. That means compared to disk drive and radar, disk drive is the highest priority. If it is the highest priority, making this mask register, put the value equal to 1 1. In this case, put the all the values equal to 0 0. Because we are servicing first highest priority source, we are received highest priority signal, so that the CPU will respond to that highest priority requesting signal. So that in radar also requesting, but this value in this register equal to 1, but in this case this is 0. So this particular case, again this 0 1 is transferred to this one and this one is transferred to this place. With the help of this one, again the value is generated like this. So in other cases, disk drive is not requesting service, this printer is requesting service. Printer and radar. In these two cases, printer value equal to 1 and radar value equal to 1, because these two sources are requesting service. In this case, this disk value equal to 0 and this keyboard value equal to 0. In both cases, the mask register will check the priority basis, which is the highest priority. Compared to radar, again printer value, printer source is the highest priority. So that the making this masking bit equal to 0, remaining all values will hold logic 0. That means like this. So now these two values, so this means 1 in this case and this value equal to 1 1. So these two are the 0 zeros. So this AND gate will receive 1 1, output equal to 1. That means I1 is received interrupt signal. If it is received signal, the values of the priority encoder, this is 0 0 1. Previous values are 0 0. Cancel these two values. Now present values are I1 values are encoder values are 0 1. So XY values equal to 0 1. That time another output is enabled. IST goes to 1. If interrupt signal is received through this priority encoder, automatically interrupt enable value equal to 1. With the help of IST and enable this one, this line and this line, this AND gate value equal to 1. If AND gate value equal to 1, that particular request is requesting a service of the CPU. Until unless CPU will not receive any interrupt signal. If it is recognized, that particular interrupt is received. If it is recognized, CPU will respond through this interrupt acknowledgement signal. If it is equal to logic 1 and another two inputs are, one is from IST, another one is the IEN. So output equal to 1. So if it is goes to enable state, that is a logic high state, the particular vector address will be generated. Vector address is generated, that address is connected to the CPU. CPU will receive the vector address, so that the processor will respond to the that particular vector. Cursor will respond to the particular address, that vector address. Cursor again will start the execution from that particular vector address. Again cursor goes back to the mainline sequence after execution of all these instructions. This is the way we are going to perform parallel priority interrupts. So coming to this one, in this case we have 4 inputs, that means priority encoder inputs, that means I0, I1, I2, I3 and XY, IST. These are the 4 outputs. This is IST and XY outputs, IST output and XY output. So if I0 is requesting some service, that means remaining device I1, I2, I3 is received or not. That means either requesting service or this device is not requesting service. So either 0 case or 1 case, the processor will respond to this particular input. That means because this is the highest priority. So in don't care means either requesting or not requesting, because the processor that hardware is respond to this I0. So remaining values is represented by don't care. That means don't care representation is represented by either cross symbol or D. So that the processor will respond. That time this XY value is generated, output equal to 0 0. So this is 0 0. So if interrupt is recognized, that IST value equal to 1. Same as it is in I1 case, if it is a received signal, that means if it is I1 is received, that time compared to these two, I2 and I3, I1 is the highest, so that if it is requesting some service or not, whatever the case, but I1 is requesting service, that time I1 is received with the help of priority encoder. Remaining two cases, this is the invalid. So in this case, I1 is the highest priority compared to these two, so that these two values is represented in don't care. So I0 is not requesting some service. In this case, the xi value equal to next sequence 0, 1. So any case, if the interrupt is received, then output is enabled, that time the interrupt status flip-flop will goes to enable state. That means IST, this one. So like this, I2 is the highest priority compared to I3. I3 is the lowest priority. If there is no device is requesting some service, in this case I3 is only requesting service. That time this XY values will goes to 1, 1 state. That time also IST value equal to 1. If no device is requesting signal, requesting to the this hardware, that means all the device values should be zeros. So here XY values is don't care values. There is no output, there is no requesting signal, so highest value equal to 0. With the help of this Karnaugh map, we are going to two variable Karnaugh map, we are going to generating these three output values, I0 bar and I1 bar, I0 bar, I1 bar plus I0 bar, I2 bar, like this, IST, I0 plus I1 plus I2 plus I3. These are the three output functions. Coming to the final block diagram, final tabular form. In this case, a CPU goes through the interrupt cycle. CPU goes to interrupt cycle. So that means this explanation. CPU goes to interrupt cycle if both inputs IEN flag bits, interrupt enable and interrupt status bit are both are equal to 1. So what will happen in this case? Stack pointer is decremented by 1. That means this is the mainline sequence. If interrupt is occur, in this case, previously cursor is executing like this. So interrupt is occur, the actual execution of the mainline sequence is break, the cursor goes to another program. That means it goes to the vector address location. So it starts the execution from this instruction. It executes all the instruction in the subprogram. After completion of this last instruction, cursor goes back to the mainline sequence and it executes the remaining instructions in the main program. So what will happen if interrupt goes to another location? That means previously program counter is always it is advanced and it is pointed by the next address location. This address is shifted to the stack pointer. That means stack register, stack memory is the temporary storage register. Previously stack pointer is always points to the top of the location in this case. So if interrupt is received, cursor goes to another vector address so that this value is pushed into the stack. If it is a 16 bit, that time if it is a byte of information or 16 depends upon that location. So this value is pushed into the stack's memory. This is a stack. Stack pointer is decremented by 1. It points initially there is an address stored inside this top of the segment, this top of the data, top of the stack segment. So this temporarily this address is stored inside this location. Coming to this one, the PC is held by new values. The PC value, that means vector address value. So stack pointer is decremented by 1. The PC is stored into memory of stack pointer. So this one, the second case, the address is stored inside this location. Coming to this one, interrupt acknowledgement signal is enabled. Enabled interrupt acknowledgement signal. So from this, interrupt acknowledgement signal is enabled. Interrupt acknowledgement is enabled. Next one, the valid vector address. Vector address is generated. That vector address is pointed by PC. Previously PC is pushed into this address. Now PC register will hold the vector address. So interrupt enable goes to 0. So if vector address is pointed to a PC, automatically PC is pointed to the vector address location. So that time the particular task is completed. That interrupt enable is goes to disable. Interrupt enable is goes to 0. That means it is waiting for the is there any interrupt sources is requesting some service from the other sources. It is ready to accept. If it is goes to 0, the device is ready to accept another requests. So here disable further interrupts and go to the fetch instruction and go to the next instruction, fetching option, fetching cycle. So this is the way we are going to performing parallel interrupt recognition in the form of priority. Thank you.